This is a continuation of a video that's for HSC or Year 12 Engineering Studies, and we're looking at Chapter 2, which is on transport. We're continuing from, we've just looked at heat treatment, and we're now continuing on with manufacturing processes for ferrous metals. So you'll remember in Year 11, I created this post where I talk about how there's different fabrication methods. There's three main families of fabrication methods. We have forming, casting, and joining. I would say cutting is also another part. So machining or milling, it's another consideration, but that's not on that list. So it's easy to forget. But in the Year 11 book, if you go back to the Year 11 textbook, they do have some mention of things like turning and knurling. So knurling, if you have darts will have that rough texture around them so that you can grip them. That's called knurling, with the silent K. But what we're going to focus on today is we're just going to focus on forming, and potentially I'll have my pause and get some notes for joining. I'm not going to talk about casting because I have already made a video on casting, and I'm pretty happy with that video. So let's look at forming. Within forming, there's this picture has 4 main areas of forming. So we have forging, and if you have to give an example of forging, I usually say things like spanners. So I have some videos here that I would have shown you last year. So I have forging a spanner, and I have drop forging, and forging is just where you hit things with big machinery. Before there was big machinery, blacksmiths would forge with a hammer. They would heat things up. So they've taken the red hot blank, and ready, 1, 2, 3, boom. That's how they forged it, right? And that's going to press it into shape. So in cars, the crankshaft in a piston is exactly what I was thinking of. That's a good example of forging, and we have some of those. We have some forged blanks that haven't been cut away in the back of the room. So that's forging. We have another one here. We see some more drop forging in this video. That object is just being forged by big compressive hits. You can hot and cold forge. It's far more common, I think, to hot forge, but it is possible just to beat things into shape with some materials. You can just beat into shape when they're cold. Panel beaters are more likely to. You could consider what they do as being cold forging. I feel as I'm going a little bit out on a limb by saying that, but I'm going to keep it and let's move on. Okay, so the next one that we're going to look at in our book. So, here's the important part of forging. I knew there's something really important with forging. When we forge, we really care about the grain structure, the grain flow of the forged material. Now, I should have a picture here, but I can't see it straight away. So, let me just look one up. Grain flow forging. Now, last year, I almost certainly put a question, bless you, I almost certainly put a question in your prelim, bless you. I almost certainly had a question where we talked about hip stems, right, in the Year 11 exam. Did I do that? Yeah, it's one of my trademarks. So we have a look at these pictures here. We can see that if you just machine a material that's come from a rolled blank or a drawn blank, you're going to have all of the grains be flowing more or less in the same direction. And that's bad because when you machine, you're going to have points of weakness. In this case, you'd have a point of weakness here. Whereas when you forge, the grains are going to flow around the object. In the back of the room, I've passed these objects around. You're getting close to a COVID test there. But in the back of the room, we have a sample that has, that you can see the cross-section, you can see that forging, that grain flow. But we'll just have a quick look at some diagrams. So here we can see that the, I think this one, I do think it's flowing a little bit around the corners. I'm going to say that's been, this one here, you can clearly see that the grains flow around that shape. This one here, really obvious that you can see. I've seen this one in, I think, past trial exams. So here we can see the difference between a machined part and a forged part. We can see here that we're going to have much stronger points here and here than we will there. Right, so in that machined part, we're going to have a definite point of weakness. Again, just to make that diagram really clear, we can see forging, we showed the grain flowing around the object, whereas If we machine, it's just straight across. Like I said, we've covered that in the prelim, so I'm not too concerned about going into any more detail than that. The next is rolling. Now, I've used my chameleonaire joke already. I did just show my students that the video 1979 starts off with the setup for that joke, which is someone rolling in giant wheels. But we're not going to show that now because I don't want to get this video demonetized. Yeah, because of all the money I make off these videos. Anyway, so what we're going to look at is there is a big difference between hot and cold rolling. And it's a little bit counterintuitive because we expect that when we have hot rolling, we expect that heat to mean we're going to have larger grains. But no, in actual fact, when we have hot rolling, we're going to have equiax grains, and cold rolling, we're going to have, like we would expect for work hardening, longer elongated grains that are proportionally larger. So let's have a quick look at this video that will go into that. This video I showed you when we learned about grain growth way back when, and we looked at it to see examples of, in this video they show tempering, they show ISOD tests, they show normalizing and annealing. It's a pretty good video. I really like this video. And what we're going to look at here is that they've taken this sample, and we saw the sample originally had equiax grains, and now that when it's rolled, what we're going to see is the difference between those. We can see clearly that the cold work section has elongated grains. Now, elongated grains, I'm not going to go into too much detail, but are not great. For the same reason that we don't want to have machined parts, elongated grains aren't going to have bidirectional strength. We want the steel to be strong in every direction. So what we want to do is to return, we don't want to increase the size of those grains back to its original shape. That would be annealing. What we're going to do is we want to have the grains be small to stay small, but we want them to be equiaxed. So what we often do after rolling, well, okay, so the video is going to show that here we have our grains. They're large grains. So that might be from an annealed blank. And then we can see the elongation in those grains. And then this video is going to show, so here we have elongated grains. We're going to heat up to the recrystallization temperature. You're getting at 300, I think that's a typo. I think that temperature should have been going up that whole time. Oh, anyway, they've gone up to the recrystallization temperature, and then once they've gone to the recrystallization temperature, we can compare. So what kind of test would this be? Probably a Rockwell hardness test. It doesn't use a ball, right? And this is a tensile test. This is how tensile tests used to be done. And they're comparing the relative strengths. So what they're going to do now is they're going to show that they're showing the different iron-carbon diagram, and they're going to show the process of normalizing. So yeah, heating up to 750, then allowing to cool in air, and the result is smaller equiax grains. Yeah, so that's the process of normalizing. Do you see how did they cool those samples? They just took them out of the furnace and let them cool in the air. Yeah. Okay. Then after that in the video, they then go on to show tempering. So that's hot rolling. Sorry. I'm sorry, I made a mistake there. Cold rolling. With hot rolling, we don't need to go through that secondary process of normalizing. It's already going to have equiax grains. Now, what are the advantages and disadvantages of these two methods? Well, effectively, I mean, it says advantages and disadvantages, and here it says advantages. They're just literally the opposite, right? So advantages, here's the advantage. There's less stress in the machinery, right? So you don't need as powerful machines. These days, that's not as big an issue, right? These days, powerful machines, not that hard to come by. And it leaves an unstressed finished product. Okay, well, that can be useful if you need something that's tough. Generally, we're okay with making the steel a little bit stressed, right? The same way we're okay with students being a little bit stressed, because, you know, stress is what turns rocks into diamonds, as they like to say. Okay. The disadvantage is that it's not dimensionally accurate. When you hot roll, it warps the material. Yeah, it actually comes out more than a millimeter out of shape. It also comes out with this scale on it, right? It actually looks like kind of like burnt wood, or it looks actually, I think, like scale, like let me just get you a picture rather than me trying to describe it. So, hot rolled scale. Yeah, milled scale. You can see it leaves this scale on the outside that needs to be then machined off, right? Or typically will be machined. It's not a good thing to have that scale on the outside. So that's a downside, that you not only does it warp, but you can't reliably get the dimensions, and it will leave this scale. So these days, most rolled sections are going to be cold rolled. And let's look at with cold rolling. It produces a harder product that is more dimensionally accurate. So it's not stress, it has stress, but that means it's going to be harder, and it has a more presentable product because of lack of oxides, which means it doesn't have that mill scale on it. So I have definitely had past trial questions where I've asked students to be able to identify, is this hot or cold rolled? Yeah, which process is taking place here, right? So be prepared to be able to answer that question and be able to talk about the advantages and disadvantages. I've already said I'm not going to talk about casting in this video because I have another video where I've already covered that. So we're now on to direct and indirect extrusion. Now, I haven't seen many questions about this, so I'm going to say that this is low probability. This is really more this is a focus for extension students rather than for everyone. But the idea is that you can, typically when we think of extrusion, right, we think of direct extrusion, where you just push from the back, right? The idea there being that if you have toothpaste, most people squeeze their toothpaste by direct extrusion, by rolling up and squeezing from the back and pushing the tube out. But it is also possible to squeeze from the front. Now, why would you do this? Right? Okay, so let's see if I can find specifically. Direct extrusion generally requires more effort, so it's used for more ductile materials, right? Indirect is used, it has lower for alloys with lower ductility because the equipment is more expensive. Direct extrusion is used where possible. Okay, both of them are hot working processes. Both of them are hot working. Now, what do we extrude? What are some examples of things that we extrude?
Toothpaste.
Okay, engineering materials. So the answer was toothpaste. Window frames. Rails. Rails are rolled, typically.
So engine blocks are cast.
The engine blocks are cast. Okay, so window frames is the answer I like. But it's also important to remember tubing can be extruded, right? So that's another option as well.
Other than window frames, it's like common.
Tubing.
What tubing is in one?
Handrails.
Oh,
yeah.
right. Okay.
Especially if a handrail that's got like a non-circular shape, that's going to be extruded. Yeah. Okay. If we go back here to extruding rods and tubing, drawing rods and wire and tubing. So we can do both, and so there's a very, very close overlap between drawing and extrusion. And so somewhere in between, we're going to look at this amazing video, which I was just told, if you don't like this video, maybe engineering is not for you, where the engineer guy, right, he does some great videos, really like his videos. And what he talks about is the process of cans. He talks about why cans. He says, well, cubes or cuboids, right, so a rectangular prism, they would obviously be better for space, whereas spheres are better for stress, but cylinders are a nice compromise between the two. How they start is they start with a punched aluminium sheet, right? And then they put it in a drawing die, and they draw it by making this cup, and then they just start thinning it, right? The punch presses through and redraws it to make it smoother and smoother, right? And every time it takes a little bit of the thickness off. After that, it puts a dome. Why is the dome there?
The dome there is to reinforce the bottom.
Reinforce the bottom, yeah, because well, yeah, it's an arch. It's an arch. It's a rotated arch. Yeah, it's a rotated arch. Anyway, so I'm not going to go through this whole video because, you know, watch this guy. I'm happy to redirect and give you that guy some clicks because he does some great work. I'm happy to see him make some money from monetizing. Okay. So impact extrusion, right? So in this case, what we typically think of, well, when we think of extrusion, right, we typically think of something being we think of these two, right? Typically we think of direct extrusion, but it is also possible to get this. It's similar to our direct extrusion we just saw above, but rather than pushing from the inside, it's pushing the shape around the die. Okay, so now we're going to move on to powder forming, also known as sintering. Sintering is part of the process of powder forming. Now, with powder forming, what kind of powders are we making? Metal powders. Now, we have learnt in with ceramics that there is you can form things out of powdered ceramics. So alumina is used. You can use powdered alumina to create things. But what we're going to focus on here is we're going to focus on powder metallurgy. So what we do is we take metals, powdered metals, right? We take up ground up pieces of metal, and what we do is we squash them together into the shape that we want. Now, there's three main steps to produce this, right? Step A shows the particles in their free state. So you take the powder, and then step B, you cold weld them by pressing. Now, it is interesting to know that you could just take two metal rods, right? If you had two metal rods, if you clean them perfectly, you can join them together because metal is just metal stuck together, right? At any point, it's just metal. The reason, why does that not work normally? Why can you not normally just take two metal pieces of metal and just stick them together and they'll join?
Too cold because the particles are just not moving fast.
Okay, so I've got some great answers here. But the reason why, if I just take two pieces of aluminium, if I take two aluminium rods and stick them together, why they won't fuse is because the aluminium forms, as soon as you produce aluminium, it's going to form an aluminium. You got it?
What?
I've got a student, yeah?
An aluminium oxide.
Exactly right. An aluminium oxide forms on the outside. And that aluminium oxide, it won't join. So theoretically, if you can clean it and get it on before the aluminium oxide forms, you can just join two metals. Or what you can do is you can join them in a vacuum. Now, I didn't set up a video for this, but you can find on the internet, you can see vacuum. You have to clean it pretty close. There you go. So you can cold weld, right? He's not in a vacuum, but it might be a material that doesn't produce, so this iridium perhaps doesn't produce an oxide very quickly, and that might be what allows it to cold weld. Anyway, so I'm not going to focus too much on that. That's not my focus here. The point I'm saying is that when we fuse these metals together, we can actually cold weld them together by... We can fuse weld these things together. Now, what we're really interested in is we're interested in the sintering process, right? The sintering process, let's go there. Once pressed, the item is sintered using a non-oxidizing controlled atmosphere furnace, right? So remember, we don't want the material to oxidize. Oxidizing is bad because that's going to prevent those things from joining. The temperature allows atoms to diffuse between the grains, producing a homogeneous grain structure. So effectively what you want to do is you want some of the atoms from this crystal or this grain to jump across into the atoms of that crystal and vice versa. And that actually causes the two grains to join at the atomic level. So that is the process of powder metallurgy, right? That last step where the atoms transfer, where we heat it up in a controlled environment, the oxidized controlled atmosphere furnace, allows that transfer of atoms between the crystals, and that is what gives us our final sintered product. Now, where do we use powder metallurgy? Yes? Happy Meal toys is the answer I want you all to remember. But you could think about watch parts, right? So what we want is things that need to be very detailed, very mechanically precise. The size needs to be very accurate. They can be things that need details, like we don't have to machine a Happy Meal gear. No one wants to get on the lathe and machine out a Happy Meal gear. But with the Happy Meal gears, they don't need to be very strong. Unlike gears in a car, which need to have both hardness and toughness, the Happy Meal toy is not subjected to high loads. And because it's not subjected to high loads, we can just use powder metallurgy to get that very exact, precise shape Somewhere I have some samples. I think they're in my desk that I'll bring up and show to you. I have some samples, maybe they're in that cupboard, of some powder metallurgy. And you can actually snap powder metallurgy or sintered metals. You can just snap them between your hands because they won't survive to high impact loads or to direct force. But they have some other applications. Sometimes you want things to be porous. What does porous mean? Little holes. Yeah, porosity is a measure of how many holes, how many voids there are in an object. This can be useful if you need to lubricate things because it means that you don't have to get inside the parts. You can just lubricate from the outside, and the lubrication will move through the metal itself because it's got porosity. Okay, complex parts. So some shapes are too difficult or costly to mass produce, right? So in the case of Happy Meal toys, because of their size and complexity, they're just not viable for machining. Okay, parts that are difficult to machine. So some materials can't be machined easily. Tungsten carbides can't be machined because they're so hard. So we need to form them through powder metallurgy. Also, some metals don't go well together. So sometimes we want to have things like copper and silver alloys, right, where we want to join these metals together. They won't alloy. Sorry, they're not actually alloys, but yeah, won't alloy together, so we can use powder metallurgy. So copper provides good electrical conductivity, while tungsten provides resistance to oxidization and wear. So if you want to combine copper and tungsten, you could use powder metallurgy. Okay, so what are their advantages? Well, aside from what we've already talked about, that they're self-lubricating, they can be made into complex shapes, and some materials need to be powder metallurgy because they can't be machined or they won't alloy. The other advantages we look at, once we've got the parts, the machinery set up, they're relatively low production cost. So it usually has a high investment, but then low individual cost. Single products used in automatic expensive to set up. There's also very little waste, right? So any powder that isn't used can be cleaned up and put back into the mold. So that's another advantage. These days, we recover a lot of material from machining anyway, so it's not as much of an issue as it would have been in the past. But there's still another process where that machined tailing would have to be recut. Okay, looks like we're going to have time for welding, so I'm just going to quickly pause while I get the welding notes ready. So lastly, I'm going to talk about welding, and I'm not going to talk very long about this because I have Year 11 videos that are available that thoroughly cover welding. What I'm going to say is that there are 4 main areas of welding you should be aware of. There's 3 versions of arc welding. There's the most commonly referred to as arc welding, which is probably better known as shielded metal arc welding or stick welding. And there's 2 other arc welding methods which both use inert gas to protect the weld, MIG and TIG. There's a version of welding that just uses flammable gases, which is called oxy and fuel welding, or oxyacetylene welding is probably the most common fuel. Now, it's really important that you can draw a weld, so that here I have a picture of a cross-section of a weld, a cleaned up and etched weld. And welds will be often be X-rayed, sometimes gamma-rayed, to tell whether or not there's been full penetration of the weld. And it's important that you will have to be able to draw a weld. So this is an answer from a question from 2014. I usually have the question as well as the answer, but this is an example of an answer from 2014. And we see that's for a fillet weld, and this one is for a butt weld. It's important that you not only can be able to draw this weld, but also you understand the drop-off of strength. Now, there is a table that lists some different welding methods that I'm not going to go into. Now, there's a table in the Copeland book on page 125 that goes through some details of different kinds of welding. Now, I would suggest that this is really extension based on past HSC questions and these sorts of things. I would say that as long as you're focusing on, so here we have electric arc welding, which I referred to as stick or shielded metal arc welding. I think it's a much better way of referring to that. There's MIG and TIG. There is plasma welding, which we have a plasma cutter over in the metalwork room. We have oxy welding, but the other ones, in terms of bronze welding, seam welding, butt welding, it's important to understand that we will often use spot welding and we have a spot welder in the other room. The spot welders are used for making things like mesh and like steel mesh. What we can use is we can use it to join two sheets of metal, or in this case I think it's probably joining 3 pieces of metal, by just fusing them together directly with impact, so the machine comes together and it fuses them. So you can see the cross section there that we get molten metal which fuses the 2 sheets together. Obviously it can only be used in thin applications. Let's see, mesh. So mesh will be joined by spot welding, and that's one I think that's worth mentioning. But the same principles apply for butt and seam welding. They're both pressure welding methods. But I'm not going to read these through or go through them in any more detail. I'm going to direct you to my other video. I'm going to say that you can read this table, and you should be, for homework, I will ask people to draw a cross section of a weld and to describe its the relative strength through that cross section. One other thing I want to talk about before I finish this video on welding, though, is I want to talk about martensite, and that is that you do not want to. I'm just trying to see if I can find a question on why you don't want to weld high carbon steels. And I thought I had that posted here. I'm disappointed I don't see it right now. But there was definitely a past question. I'm going to pause for a second. So I found the question. It's I should correct that I said earlier that the drawing, the fillet weld that you need to draw, was instead from the 2017 paper. It's question 25, BII. Okay, so first of all, it talks about here, it says that you might see a warning that says heat treated. Do not weld chassis or drill flanges unless authorized. So if we look at the answer for that, we can see that the problem is that we could have martensite form, and that could produce some problems. So as it's welded, after cooling, it will tend to form columnar grains. It's not desirable. It may cool at a rate in which martensite may form, which produces a hard and brittle microstructure. And the flanges should not be drilled, as this produces stress raises, surface roughness, and around the hole, which initiates fatigue failure. So that's a pretty detailed answer. For me, I would be happy to say if you weld high carbon steel, you might form martensite, and that should be done very, very, very carefully. And so it would require a trained professional to do that. So we talked about before that there's a drawing that asks you to be able to draw, use a diagram, draw and label the microstructure, including information surrounding the chassis rail and the reinforcing plate, which the answer we provided was here. Also, while I'm on this paper, there was a question I liked, which relates to what we've just done, which it says, gears in automotive processes can be manufactured using ferrous alloys. Okay, so an iron-based alloy, usually a iron carbon, so something like steel. So sand casting and powder metallurgy are both methods can be used. Compare those two. So we would say that sand casting provides greater strength, but it usually needs to be machined, whereas powder metallurgy provides a high detailed finish, but it maybe doesn't. It has some other advantages, like it could use more complex alloys, but it more likely is not going to have the same strength. So let's see what their answers say. I did have that answer open a second ago. Here we go. Okay. Sand casting has a porous surface finish, so it would need to be machined. It can produce columnar grains if not poured correctly. Whereas powder metallurgy, it can make can make a range of alloys that are impossible to make using conventional methods. Yep, okay, so it can make shapes that otherwise wouldn't be produced by sand casting. It has a very high dimensional accuracy to what was intended. It can be self-lubricating. I did mention that. It doesn't talk about the lower strength, right? But that's fair enough. There's 4 marks. The answers could include these things. The next question is, it says, after the manufacture of gears, they are case hardened. Describe the process of case hardening. So in the previous video, which I made fuse these 2 videos together, I talked about case hardening. Describe the process of case hardening. So you heat the steel up in a carbon dioxide rich environment. It causes carbon atoms to be forced into the iron lattice and produces greater strength and hardness. Let's see what answer they provide. They say case hardening involves heating to red heat in a carbon-rich environment. Could also be nitrogen. I'd call that nitriding, but fair enough. Okay, so it can then be quenched. Martensite will form. The outer case becomes harder and wear resistant, while the inside remains soft and tough. The gear can be used in the outer case, either being martensitic or tempered back to improve its surface toughness if it needs to. Okay, so there we go. So that's what they've said there. Yep, that's where I'm going to leave this video.